Okay, great. Okay, so thank you very much, Matt, and thank you very much, organisers, for inviting me to give a talk today about climateprediction.net. Unlike, I think, other projects that we've heard about so far, CPDN, which started off as a single project, has really developed into an infrastructure, a program, and you'll hear about the fact of how we've slightly changed in terms of supporting other projects through our infrastructure. I'm presenting on behalf of a very large number of people that make up the contributors to the core of climateprediction.net, both within engineering science, the Environmental Change Institute, and in atmospheric physics in Oxford, but also at the UK Met Office, the European Centre for Medium Range Weather Forecasting, but most importantly, our moderators and our public volunteers. So, of course, climate prediction, as it suggests, is all about climate change. And we've seen, plots like this about global average temperatures. We've seen that they've been rising dramatically since the pre-industrial times. And of course, this is the average temperature. That led, of course, to the signing of the Paris Agreement as a way through the Conference of Parties to limit global mean temperature rise to 1.5 to at least 2 degrees above pre-industrial, with an effort to limit it to 1.5 degrees above pre-industrial. So from our point of view, these are two figures that you'll hear later on that are incredibly important. What's going to happen when we get to these levels? One of the things that this has done, of course, is led to a whole raft of countries that have signed legally binding agreements around net zero emissions, so stopping the emissions of greenhouse gases and particularly CO2. And you can see here that this is, a significant number of cities, but also and countries have signed up here. But as I mentioned earlier, this is an average temperature, and it's very clear that, of course, the individual changes, and here we can see a plot from NASA that showcases how the temperature has changed over the last 50 years in some great detail over the Earth's surface, that some places are seeing much greater changes than others. And of course, from that point of view, therefore, they see much greater effects from their climate change in terms of weather patterns, weather events. And we'll talk about that later on. So what do we do within, how do we actually do things like create these plots? How do we understand climate change? And of course, climate change has mostly been, and weather particularly, has been a problem very much of large scale, high performance computing facilities for many years. We can see here the UK National Met Office high performance computer in the bottom left, European Centre for Medium Range Weather Forecasting in the centre, Chinese HPC facility on the bottom right, Japan and Germany. All of these are able to do very high resolution climate simulations. The issue being, of course, that when they do that, they use an enormous amount of resources. And as such, you only really want to run these simulations a small number of times. But of course, that gives you an issue because it makes it very difficult to allow you to understand uncertainty. Miles Allen within the Department of Physics within Oxford realized this, and after talking to David Anderson, realized that actually one of the things that you could do if you appropriately scaled the computational model that you were trying to distribute would be to use distributed computing, and in that case, the forerunner of BOINC, but eventually BOINC, to actually distribute Met Office simulations. So how do we do this? Of course, it requires our project scientists to be able to split their problems up into small individual work units that through our core infrastructure, we distribute out to our citizen scientists, our volunteers around the world. What the result of this is that we can generate very large ensembles of simulations with this framework, which in reality are data limited by what the researcher is actually willing or able to analyze when they get the results back, and often what they're able to store in scale of results. So one experiment at the moment, for example, will generate about 1.5 terabytes of data per day when we're running at full steam. So you can imagine, as you'll see later, we've got a very large number of parallel research experiments ongoing at the moment, and 1.5 terabytes from each of these, we generate vast amounts of data. Our volunteer network is enormous. We've had over 650,000 people volunteer, well over 650,000 people volunteer now from all of the continents of the world. We've got 17 research collaboration centres around the world here, the white dots that are linked back to the UK centre. We've had well over 40 sub-projects funded from pretty much all of our collaborators around the world and here in the UK. We've done nearly 300 million model years of simulation. We've been running now for nearly 17 years. From that point of view, we are a very, very well-established project with a very well-established volunteer base and a great idea of how we want to use the facility. For the vast majority of our time, though, we've done two particular functions. Climate prediction was our core project, and a new project called Weather at Home, which was initially funded by Microsoft. And through all of these, we've done derivations of the Hadley Center Met Office models. That's either been coupled ocean atmosphere models in the case of HAD-CM3, or atmosphere-only models in the case of HAD-AM3P and HAD-RM3P, which was our regional model, the foundation of Weather at Home, or our most recent Hadley Center model, HAD-AM4, which has allowed us to do almost regional resolution modeling, but at a global scale. So we've stepped up the facilities that we've been able to provide. The other thing we're doing with HAD-AM4, our new global atmosphere model, is actually investigating the addition of what's known as a slab ocean onto that to give ourselves some capabilities around ocean atmosphere coupling. So what do we do with these models at the moment? Well, we've got three main experiment types. The first and most prevalent, as you'll see in publications later, is what's known as this extreme event attribution. And this allows us to make quantitative statements actually about how much the risk for some effect of some extreme weather event has changed due to climate change between now and the past, or from climate change from now to a future scenario. And this is incredibly important, as you'll see later on, in terms of some of our impact work. The next two are actually looking at improving the quality of climate models themselves. So bias reduction, so understanding how or why climate models might introduce biases that deviate away from observed, historical observed scenarios. And so we can change the parameterization and things like that within the model. And then finally, climate sensitivity studies. And this allows us to really perturb all of the parameters as input into the models and see actually how well we understand how the model deviates with those perturbations. But there are things that we can't do or couldn't do from CPDN. We can't do seasonal forecasting of the weather. So the Met Office models are not forecast models. And we don't do fine scale climate modeling at very high resolution. But what we've done over the last few months, about 12 months, particularly through the COVID pandemic, is we've actually introduced a new model into the system, OpenIFS at Home. This has actually come from the European Centre for Medium Range Weather Forecasting. So we've actually changed model supplier in this case as well. And this is the open source version of their integrated forecast system, which is what they actually use in production at super high resolution on their HPC system to actually run their medium range weather forecasts. And this will give us some new capabilities. We can actually look at the predictability of weather forecasts. So we can look at improving the skill, which is a weather forecaster's measure of how well they're actually doing in forecasting. We can look at probabilistic forecasting and actually try and look at uncertainties with nonlinear atmospheric interactions. Again, these are sort of perturbation studies that can be supported. We, of course, because we've got past data from the European Centre for Medium Range Weather Forecasting, we're going to be able to actually explore past weather and climate events. So looking at how a particular tropical storm developed or something similar, we can actually see, well, okay, you know, how unusual was it that that scenario happened? If we run 100,000 of those, of that particular scenario, you know, actually, was it just pure chance that it followed that track, or was it something that was more inherent? And finally, of course, you know, OpenIFS has a reasonable community of users. This is a production software platform, which means that anything that should run on OpenIFS should be able to be run on OpenIFS at home. You know, we've obviously got some resource constraints because we are running in the volunteer network, and that includes our resolution. So we're running at about 127 kilometers vertical and horizontal and vertical resolution. So from that point of view, you know, we've got a little constraints, but we should be able to run the same sorts of experiments. But enough of the new models, you know, which is an interesting thing. What have we actually been doing scientifically? Well, I mentioned earlier about this idea of attribution and impacts. And one of the key things that my own research group have been doing within and using CPDN for is actually looking much more at the relationship between extreme weather events and impacts. Looking at, you know, if you have heat waves, droughts, floods, storms, and fires, actually, how does it affect us as people? That might be our health, for example. We've had projects looking, or trying to get projects going, looking, for example, at Zika virus and the spread of Zika virus due to increasing amounts of heavy precipitation. With infrastructure, well, you know, the energy system, you know, has significant new requirements on it, where we see increased heating and cooling requirements. But also, does the energy system work as well if we have high temperatures, high precipitation, ice storms, things like that? And you can see in that picture that whoever installed that railway system wasn't really realizing that the system was going to get so hot, and the rails have buckled quite significantly. Of course, food security, you know, economics around this, business insurance, and we have a new center on greening finance and investment in which we're participating. And finally, migration. So looking actually at how people and animals move around because of increasing extreme weather events. As a whole, since 2019, so we've actually had a very successful academic period. I highlight all the papers that have specifically used CPDN data here. On the top right-hand side of the 21 contributions to the 2020 Bulletin of the American Meteorological Society, 4 use CPDN generated data, which was our highest total to date. On the right-hand side, for the European Geophysical Union General Assembly, we had 4 contributions, again using CPDN data. I'm going to highlight a few of the findings from some of these papers now. So if we look, for example, at Fuka et al. Around the precipitation in Mozambique, Zimbabwe, and parts of Zambia in February 2018, they've actually said that these events, you know, are 37% less likely in future due to climate change. So extreme events become rarer in some places, not become more likely. So that's one of the things that we need to understand with the impacts of climate change, of course, is everything doesn't get just more likely to happen. There are changes one way or the other. Where if we look again at precipitation, this time in South America, well, you know, that here the outputs from this paper, this was Lee et al. Looking at rainfall, dangerous extreme precipitation in South America. We can see actually that, you know, these extreme precipitation events are going to increase under future warming. And worryingly enough, their changes are going to be non-linear. So it's not going to be a nice linear change in the volume or number of or frequency of these events if we move from 1.5 to 2 degree warming, bearing in mind we're at 1 degree warming already, but actually a non-linear relationship. So huge increases once we get into the 1.5 to 2 degree scenario part. If we look at Dikipuna, there we've been looking actually at global teleconnections. So can we see that some extreme events are actually related to other atmospheric atmospheric features. In this stage, the quasi-resonant amplification, QRA. Well, actually, there were two events, the Russian heat wave and the Pakistan flood of 2010. Well, we proved that there was a link between QRA and those events. So if you have QRA occurring, then you're likely to see these types of events happen. And then, last couple of papers I'll talk about, in terms of total precipitation here, looking at, under both 2 degree and 1.5 and 2 degree warming scenarios, winter precipitation extremes can increase over 80 to 90% of the Northern Hemisphere. If we stay at 1.5 rather than 2, we reduce the average magnitude of these increased events by only 1.6 to 2 times. So we're still going to see significant activity and significant changes. And then finally, a paper I was involved in actually looking at the Australian bushfire risk, looking at through 2019. And actually, these type of bushfire risks have become more likely by at least a factor of 2 due to the long-term warming trend that we've seen. So if you're in Australia, and Marcus was earlier, don't go outside with the Barbie when you have a high fire risk of a fire weather index, because there's a significant danger. So I mentioned earlier that CPDN is a framework. What we actually do is we participate and collaborate with other projects to actually do their science. So we provide the computational infrastructure, the data that they actually use to then produce their science. And I've highlighted there are 8 new projects that we've got since 2019. And I'll just, a couple of these are highlights, Arctic Connect, looking at the effects of the rapid Arctic warming on European climate and extreme weather. You saw in that plot earlier from NASA, the band and the right in the most northerly part, had the most extreme change in the last 10 years. 4C, well, looking actually in terms of future emission scenarios, well, actually, we want to keep to 1.5 or 2 degrees at an absolute minimum. Well, can we really quantifiably understand what effects those are going to have in terms of the global greenhouse gas emissions and hence the effect on the atmosphere? And then in collaboration with the New Zealand Met Service, Wakahura, Extreme Events and the Emergence of Climate Change project, we're actually going to be developing a new weather at home region at 25 kilometers and then running large ensembles for 3 different future climate scenarios to compare against present day, 1.5, 2 and 3 degrees. So just to finish up, because I think I'm well and truly running out of time, we are still the world's largest climate modeling facility in terms of numbers of resources, and certainly in terms of numbers of simulations that we're running. We've broadened the appeal of CPDN with the new model with OpenIFS at home, and hope that actually that will allow us to increase the number of members of the research community that we can support and collaborate with. In spite of COVID-19, 2020 was still a very, very successful year, and we've continued that with early 2021. We are collaborating globally, which does include a couple of new collaborations with people we've never physically met because of COVID restrictions, which will be a new experience. But also we've started doing something new with it. We started using CPDN actually to support teaching. And that's particularly in terms of undergraduate student projects and research dissertations for an MSc in energy systems, which I'm the course director for. The important difference here, of course, is with a research project that a PDRA is doing or something like that, there's a long timescale involved, and we can say, well, okay, if something goes wrong, it's not such an issue now because it'll be fine next month and you'll be fine. For an undergraduate project, for a research MSc dissertation, there are much smaller timescales with much tighter deadlines. We need to be operating in a production manner, and I think we've got that sorted. So thank you very much, and I'm happy to take questions.